All right. In the next three modules, we're going to go over the annealing process, starting with the first phase of recovery in this module. And this is the reverse effect of cold work, so basically undoing cold work. All right, so let's start with an overview of the annealing process. So annealing is the process to return to the pre-cold work condition before all of that strain hardening cold work was done. And so typically these treatments are done in 1 hour, but they don't have to be, but that's just kind of a standard time. And so the annealing temperature then, T anneal, is the temperature it takes to anneal for 1 hour. And so and again, the effects of cold work are nullified or removed. And there are three stages of this annealing process that we're going to discuss: recovery, recrystallization, and grain growth. And the first one we're going to talk about in this first video is recovery. But let's go over the overview. So this graph here kind of overviews the three stages and the properties within those stages. So the X axis is temperature. So again, annealing temperature, so treatment for 1 hour at that temperature. So we start with 100, 2, 3, 4, 5, all the way up to 700 degrees for this particular material. And we're going to look at the tensile strength on this axis, which is the blue. And then we're going to look at ductility, which is the red curve. And that goes from a low to high value. So initially, before we anneal at 100, we can see the strength is the highest and the ductility is the lowest of these curves, right? That's what we'd expect from cold working. And what we see is after the process, the higher temperature we go, the longer we anneal for, the higher the ductility is, this red curve, it increases, and then the strength decreases. So in annealing, we remove strength and gain ductility. So that's the point of this process. And so within those, within annealing, the three stages can be kind of classified by the different colors. So blue, orange, and red. So blue, the low temperatures, is where recovery occurs. And we can see here just from these properties that not much happens, a little bit, maybe a little decrease in strength and a little increase in ductility, but not much. And then in the middle, this is where we notice the huge dips and changes. So strength drastically decreases, ductility drastically increases. And this is recrystallization. And then finally, we see in the last step that they've kind of plateaued. So strength kind of flattens out, ductility kind of flattens out. You might get a little decrease in strength and a little increase in ductility, but for the most part, it's relatively stable. And that's in the grain growth stage. And so that's what we see. So just to, real quickly kind of summarize what's going to happen in these stages before we take them one by one. Recovery, there's going to be stored internal strain energy. This is in terms of dislocations. So this is going to be relieved, that stored energy in the dislocations, by dislocation motion. So basically we heat it up to a higher temperature and dislocation motion can occur at those higher temperatures. Secondly, recrystallization, as you might kind of be able to glean from the name, is forming a new set of grains. We're recrystallizing the structure. So basically what happens here is the formation of a new set of strain-free grains. So it doesn't have any of the internal strain of the previous grains. And they're equiaxed grains, which means they're roughly equal in all directions. So they don't have any preferential direction like cold rolling or something like that may introduce. And finally, once we've formed a new set of grains, equiaxed grains, grain growth is as it sounds. The grains continue to grow if left at that elevated temperature. And so that can affect the properties, but to a less degree than recrystallization. So this is the step where most of the properties change drastically. All right, so let's focus on recovery now. So we saw that we're going to have reduction of the dislocation density. I must mention, though, that recovery only has a minor reduction in dislocation density. It doesn't have a drastic decrease. but we do have some reduction and we do have some movement of dislocations during this phase. So let's look at the reduction, and this can happen by annihilation. And what that means is, let's look at a scenario. So if you just look at the top portion of this sketch here, you see this extra half plane, and then below it, you see the tension, right? So that's an edge dislocation. And then if you just look at the bottom, you'll notice that you have another edge dislocation, but it's upside down from what we normally think of it as. So imagine that there's these two edge dislocations, right? And they want to move along this plane here or this plane here, right? In a normal scenario. Well, if we elevate the temperature, then diffusion can happen more readily, right? We've talked about this in the diffusion chapter. And so when that happens, atoms can diffuse from the tensile regions to those tensile regions and basically cause the migration of these extra half planes. So in essence, we can kind of move these edge dislocations closer and closer. And if they get closer and closer, right, you get atoms here and here and here and here. Basically, those extra half planes of atoms will match up and no longer be half planes. They'll be a whole plane. And so it'll just look like this. And this is a perfect crystal, right? Everything is in its proper position. And so that's the annihilation process, because it's removed those two edge dislocations with opposite sign. But this can only happen if there is diffusion in that region. So that could only happen at elevated temperatures, not, at room temperature for the most part. So that's one way from diffusion. The other scenario we can think of is, let's think of, again, an edge dislocation on a slip plane. So we're saying the direction is, either left or right. And we're going to apply a shear stress. So we're basically going to move the edge dislocation towards the right in the scenario. But we also have this sort of obstacle, which is actually a dislocation that's kind of stuck at a different angle. So it can't move. It's immobile. So what happens is once that atom, if that atom wanted to move in this direction, it would get stuck at the obstacle. However, again, if diffusion is possible, then basically the atom, the extra half plane, could move and climb, what we call climb, from diffusion, vacancy diffusion, up to another plane. So up here now. And then at that point, it's free to move in the slip direction without the obstacle. So it basically moves around it by climbing to another plane. And so again, this would only occur if vacancy diffusion was allowed, and so at the elevated temperature. So these are just a couple scenarios. But one thing to keep in mind is that, here it allows movement to occur. It's not actually removing dislocations. It's just allowing them to move more freely. And then in this scenario, it is annihilating dislocations, but not the majority of dislocations that occur in the material. So that we have to save for the next phase. And so in this case, again, we could have annihilation if there was another one on that plane and they could meet and do the same process. All right, so this is kind of what's happening at the diffusion or the dislocation level. If we want to look at the microstructure, so what's happening with the grains and so forth, right? So this is a cold worked material. So you can actually tell that from all of these lines. These are known as slip bands that kind of indicate that there's plastic deformation that's occurred. So this is the grain structure. You see grains. You also have the twin boundaries, which are these regions here in black. So all of those are the grain structure of a cold worked material. And the point I want to get across here is if we're looking solely at recovery, so let's say we put it in the furnace and only recovery has happened, so no recrystallization, the effects of recovery are at this very small level, right? They're at the dislocation level. So dislocations which are on the atomic scale are moving. And so we don't frequently see the effects of recovery on this structure. So basically they look the same, right? So I just showed the same image because the microscale changes, really there aren't microscale changes that we can see in the material. So that's one key thing to kind of talk about when we're looking at the microstructure of these properties. All right, so in the next module, we'll talk about recrystallization.